So we often want to know, is it worth the effort to try to invert a matrix when they are not exactly easy to do? Um, well, quick is maybe the better word than easy. Some matrices can be really easy to invert, but they still can take a lot of time. So we want to introduce the determinant of a matrix that tells us if the matrix is singular or invertible. So we often, for a 2 by 2 matrix, will write determinant of A, B, C, and D, where A, B, C, and D are just the entries in those positions. Oftentimes we'll abbreviate by writing A, B, C, and D, but notice that this time we're just going to write with the flat bars rather than the square brackets. So this is a shorthand to say we're going to calculate the determinant. And so the determinant is going to be equal to A times D minus C times B. And it helps to visualize where this comes from. So we multiply A times D, and then we subtract C times B. So if I want to label that, it's a plus A times D, and then actually I think it was this one, we subtract C times B. So to practice a couple determinants, notice that these are the matrices that we had on the previous examples. If you recall, A was singular, B was non-singular or invertible. So if I want to calculate these, I'm going to multiply 3 times 10, or excuse me, negative 10, 3 times negative 10, and then I'm going to subtract negative 6 times 5. Three times negative 10 is negative 30. Negative 6 times 5 is negative 30. But remember, we're subtracting this. So negative 30 plus 30 is going to give us 0 as the determinant. If we come over to B, we have 2 times negative 3. So 2 times negative 3, so that's negative 6, minus negative 1 times 8. Negative 1 times 8, so that's minus negative 8. Our negative signs cancel out, and we get negative 6 plus 8, which is positive 2. And so, what kind of conclusion might we predict about the determinant of a singular versus a non-singular matrix? Well, the fact, if you haven't guessed it, is that if the determinant of a matrix is 0, then that matrix is singular. So if we get any number other than 0, like 2, or 100, or 1,000,001, the excuse me, the matrix has an inverse. So I want to show what the determinant for a 3 by 3 matrix is. This is more complicated. So if we want the determinant of a 3 by 3 matrix, let's say we have A, B, C, D, E, F, GHI. If we want the determinant of this matrix, we pick a row, usually the first row, for example. This is going to be our fixed row. I want a slightly darker color, this one. And so we're going to have A minus B plus C, but there's one other thing that's going to happen. So if I do highlighter, if I cross out A and the row and the column that have A, and when I come back to being a pen, what I'm going to get is the determinant of E, F, H, I. So this is a 2x2 determinant. We know how to calculate these. If I come back to highlighter, if I cross out the middle row or middle column and the top row, I'll have D, F, G, I. So again, the determinant of a 2x2 matrix that I'm familiar with. And lastly, if I cross out the very last row and the top row, the numbers not colored out in red, D, E, G, H, become the 4 entries of the 2x2 determinant. So this requires simplification, and it can be a lot of work, but it's also still a lot less work than trying to invert a 3x3 matrix only to find out it's singular. So the matrix I'd like us to determine is 1, -1, 0, 1, 0, -1, 6, -2, -3. And so I'm going to write the expansion of the first row first. So that's going to be 1 times the determinant of something I'll fill in a moment, minus 1 times the determinant of the second part, plus 0 times the determinant of the third part. So in the first one, if I cross out the first column in the first row, what's left over is 0, 1, -2, -3. And that's not going to let me erase it like I want to. Okay. No problem. I'll just rewrite the numbers. So it's 1, -1, 0, 1, and 6. So if I cross out, okay, so what I'm going to do is cross out, so put an X over the rows, or the column that went into each, that was crossed out to form each smaller matrix. So our second one, we're crossing out the middle row, and of course the top row is already accounted for. So we'll have 1, -1, 6, -3. Lastly, if I were to cross out the row or the column all the way on the right, we'd have 1, 0, 6, -2. 1, 0, 6, -2. now we get to actually do the computation. So here we have 0 times -3 minus -2 times -1. So that's 0 minus -2 times -1 is +2, so it'd be 0 minus 2. So we have 1 times -2 from this first part. Then we have 1 times -3 minus 6 times -1. So that's -3 minus -6. That turns into an addition. So we have -3 plus 6, which would be +3. And so we have out front minus -1. So I'm just going to say it's plus 1 times 3. Lastly, we have 1 times -2 minus 6 times 0. So we have -2 minus 0, or -2. And all of this is times 0. So when I put this together, first I'm going to say this is the next line that it's equal to. The intermediate steps were just the scratch work. So we have -2 plus 3 plus 0. And then this is equal to +1. So if this is +1, we can conclude that the matrix has an inverse. So the matrix is invertible.